Here we're going to solve a radioactive decay initial value problem. So, right, we have the differential equation. The radioactive decay proportionality constant is 0.5, and we have an initial condition of 10 units of mass. And we want to figure out what is the solution. All right, so let's go ahead and use separation of variables to solve this. So q prime, that's the same as dq over dt. That's equal to negative 0.5 times q. All right, well, if I want to separate that, I can multiply by dt and divide by q. So I get dq over q equals negative 0.5 dt. Right. Let's go ahead and put some integrals on that so we can solve this. All right, so integral dq over q, well, that's the natural log absolute value of q. There's a plus c, but I'm going to lump it onto the other side. So I have negative 0.5, so it's going to be negative 0.5 t. Then there's my constant integration for both sides. Next step, I want to solve for q, so let's exponentiate both sides. So if I exponentiate the natural log, so e natural log absolute value of q equals e to the negative 0.5 t plus c. I want to rearrange these a little bit so the e and the natural log kind of cancel, so we get absolute value of q. And then here I'm going to write this as e to the negative 0.5 t times e to the c. But right, e to a constant is still a constant, so I'm just going to write that as e to the negative 0.5 t times a constant. Right, it's nice to have my constants in front, so I'm just going to write it as c e to the negative 0.5 t. All right, next thing to do is, being really careful. I left the absolute value in, but really the absolute value will either apply, multiply the q value by positive 1 or the q value by negative 1. So it's kind of like multiplying a plus or minus. And you can kind of absorb that plus or minus into the constant. So e to the negative 0.5 t. Right, if the value of q ended up being positive, the constant would be positive. The value of q ended up being negative, well then we could multiply the negative over to the constant. You kind of can absorb it. So you can kind of absorb that plus or minus c into there, and so it ends up being just another constant still. It's e to the negative 0.5 t. All right. Last thing is solved for the initial condition, right? We can't predict how much radioactive substance there will be in the future if you don't tell us how much there was to begin with, right? That's a very important fact, how much you start with. So in order for it to predict that, we're going to have to apply our initial condition that q at time 0 is equal to 10. But I can also plug in 0 for the solution to the equation here, this general solution. So that is c times e to the negative 0.5 times 0. Well, that's c times e to the 0. That's just c. And so it turns out that the constant integration just ends up being exactly the initial condition. So the solution is q of t is equal to negative 0, it's equal to 10 e to the negative 0.5 t. And intuitively this makes sense because the limit as t goes to infinity, meaning you wait a really long time, of q of t, well, that's essentially 10 e to the negative 0.5 times infinity, but that's 10 times e to the negative infinity. So e to the negative infinity is, as the value of the exponent gets more and more negative on the e, it gets closer and closer to 0 on the positive side. So then you pretty much end up with 10 times 0. So if you wait a really long time, forever, then you're getting closer and closer to 0 radioactive substance as time goes to infinity.